Welcome everyone to the AI Research Bites. This series of short and informative talks showcase cutting-edge research work from ServiceNow AI Research team. The AI Research Bites are open to all, especially those interested in keeping up with the fast-paced AI research community, especially security now. Today's session features a 15-minute talk from Léo Boisvert on advancement on security assessments and will be followed by a Q&A. Léo is a PhD student at Polytechnique Milan and a visiting researcher at ServiceNow Research, and he's super interested in AI agent security. Today's topic. Up to you, Léo.
Hi everyone, thanks Fanny for the introduction. So yeah, as Fanny said, today we're going to talk about evaluation of agent security, and I'm going to present DoomArena, which is a framework for agent security testing that we built here at ServiceNow Research. So before we start, the mandatory legal slide, and then we're off. So by the end of 2024 and beginning of 2025, everyone was talking about how this year would be the year of agents, how agents would be deployed, and we see a lot of them being rolled out into the world. We see them doing a lot of like very easy tasks, some repetitive stuff, and we see it across the industry and also at ServiceNow. So the question is, can you build an agent that just performs well on benchmarks on your evaluation tasks and just release them into the wild? So in the beginning of the year and recently, there were a lot of headlines about risks that AI agents pose, both new risks and existing risks that are amplified by the deployment of agents. So this leads to the question of how do we evaluate it? But all of this is a little abstract, so let's look at a concrete example. So this is an example where we have an agent that's performing a customer service role. It's taken from the TauBench benchmarks for people who are familiar with it. It's a benchmark where agents have the roles of customer service representatives for the airline and retail domain. This example is taken from the airline domain. It starts with a conversation where an agent asks a user how it can assist with flight reservations. The user answers with a bunch of details and has a question about their gift card balance. So to answer the user's question, the agent invokes a tool. It's going to retrieve some information about the user that we can see here. And then it answers the user's question saying that the gift card has a balance of $98. So all of this is working well. However, in a context where some malicious users might know that they're interacting with an agent, they might be trying their luck to get a little more or to hijack the agent into doing some things it should not be doing. So this is the case we explored in this example, where the agent, the user, I'm sorry, tries to jailbreak the agent by simulating a system alert that asks the agent to issue a refund of $300 that the user is not entitled to. This is again a toy example, and it's not in the real world. But in this example, the agent, which is GPT-4o, looks at this message and believes that the user is entitled to a refund of $300 and issues this refund to the user. So this highlights how important security testing is for AI agents. This is just one example, but if we look at the trends and the amount of vulnerabilities and incidents for agents deployed in the wild, we see that it's really skyrocketing. The projections for 2025 are really, really a lot higher than in the previous years. And this really mandates the need for extensive and rigorous security testing of AI agents. So we looked at what existed out there, and what we found is that current testing and defense methods don't really cut it. So looking first at the security testing, we see that there are three big buckets that exist. So first we have ad hoc red teaming. In this case, well, you have a team that's going to look at how the agent is going to be deployed and test out a couple of ad hoc attacks just to see how the agent will perform against them. So this allows to find some vulnerabilities and assess some weaknesses, but because it's really ad hoc, it fails to achieve systematic risk assessment. Another big bucket of agent security testing is static benchmarks. Static benchmarks are going to regroup a bunch of attacks that are documented and known. So it's going to allow you to test your agent against a lot of vulnerabilities that have been documented and that are known. So you'll know that it guarantees a minimum level of security, but it's not going to adapt well to dynamic changes where the attacker can adapt to how your agent will respond and vice versa. So this is going to fail to adapt to evolving cases, which is really where agents shine and will be deployed. Finally, the last big bucket of agent security testing is dynamic benchmarks that are really focused on security. So when you deploy your agent in the real world, you want it to perform well at the tasks that it is assigned, but also you want it to be robust to adversarial attacks. A lot of the benchmarks that exist out there really decouple the security evaluation from the task success evaluation, meaning that they treat those two categories as separate. However, we view this as inadequate because we think that both kinds of testing should be part of a holistic evaluation that don't separate between these two kinds. Well, that covers the broad landscape of agent security testing. Now, moving on to the defense side, because you want to use defenses to protect your agent. So a lot of what we see is more AI to secure AI. So specifically, a lot of what teams are using to protect agents are going to be AI-powered guardrails. So for those of you that are familiar with the more technical side of things, you can think of Llama Guard, Llama Firewall, Granite Guardrail, there are a bunch. So all of them are designed to work well in a generic setting, but our testing and evaluation continues to show that they're porous and somewhat unreliable in very narrow cases where your agent will be deployed. So that's just the nature of generative AI. It's not completely foolproof, and it's very hard to find a generic guardrail that's going to work well on your specific case. So even if some are functioning well. Another problem is that they're not always being adapted. Attackers constantly find new vulnerabilities and can exploit them. So using just a static guardrail that's going to be always the same, it's going to fail to adapt to new cases that might show up. And finally, as I hinted in the previous examples, so because they are generic, they're rarely grounded in the specific risks that your AI product will encounter, that your AI agent will encounter when deployed in the wild, because they're very generic. So just to sum it up, the AI security testing and the defenses are currently inadequate. And to address this, we built DoomArena. So DoomArena is a security testing framework that's fine-grained and modular, configurable, and extensible. So let me clarify quickly what this means. So DoomArena facilitates the construction of new security benchmarks by providing some common components to define tasks that you want your agent to perform well in, attacks that your agent will encounter, and success criteria for both the attack and the tasks. So all of this happens in a user agent environment loop that we'll cover in the next slide. So the initial case studies using DoomArena, we found that state-of-the-art web and tool calling agents have a lot of vulnerabilities, and this really highlights the need for more defenses. And we found that the existing guardrail models are really not cutting it, and they're largely ineffective in specific agentic cases. So as I mentioned in the previous slide, everything happens in DoomArena within this three-way loop. So you have an AI agent that has tasks assigned to them by a user, and these tasks have to be accomplished in an environment. So in this three-way loop, we can have all of the three nodes that are attackable. So let's start with the AI agent. So your AI agent can be pretty much whatever you want. It can be the ChatGPT agent, the Project Mariner. DoomArena is agent agnostic. It allows you to run an agent in an environment and to potentially attack it. So attacking the agent might mean that you poison some samples that the agent is retrieving from a RAG database or just a database that allows it to perform better at some tasks. So you can test how robust your agent will be when some examples it is retrieving to enrich its comprehension of the user needs. You can just test how robust it will be to that. Another case is where we have some components of the environment that are poisoned. For example, if you're dealing with a web page, you might have some user-generated content that is designed to jailbreak your agent into doing some things it should not be doing. For example, if you're on a forum, you can have some posts that redirect your agent to a website that is just a malicious shopping website that's just designed to steal your personal information. And finally, the last node is the user node. So as I showed before, like in the first example, in that case, the user itself is the adversarial component. The user starts with a benign request, just looking at its gift card balance, but along the course of the discussion, it ends up trying a jailbreak method to get more refund out of the agent. So that's the case where the user itself is attacked. And I want to clarify that when you're using this framework, the attackable components are not mutually exclusive, meaning that you can have a setting where the AI agent has some components that are compromised. There is some components of the environment that are compromised, and the user itself can be malicious. So you can test in a very fine-grained way what is attacked, what the attacks are, and what are the interactions between them. So, looking at a more concrete example, this is an attack that we built and that's usable across different environments in DoomArena. So, this is taken from the WebArena benchmark, if you're familiar with it. And this attack basically just injects a pop-up that is completely benign looking when looking at its visual appearance. However, there is some hidden text inside of it that prompts the agent to navigate to a malicious web page. Because the agent in this case has access to the HTML, the computer code of the page, it leads the agent to being hijacked in around over 90% of cases. So we can look at an example of this happening. Here we see the task assigned to the agent, retrieving some products. The pop-up is displayed. And then just the step afterwards, the agent sees that it has to navigate to this malicious web page, and then it goes there. So of course, this is just a simulated environment, but it's an example of how agents can be easily hijacked based on just information that looks relevant, but is not. So looking at more results, those results are taken for the TauBench benchmark, the benchmark from which we showed the customer service example in the beginning. Here we have two settings, the airline customer support, the retail customer support, different agents, GPT-4o and Cloud 3.5, with different attacks, one where the user is malicious, the one we saw in the beginning, and another one where the catalog is malicious. This simulates an example where you would have vendors on a marketplace that inject some malicious description of their products so that when an agent retrieves details of these products, it's going to lead to some prompt injection for the agent. So very dense table, I apologize. So we have four key columns. So the attack success rate, which means how frequently the attacks work. Task success rate when there's no attack. So this is just the baseline of how the agents perform in this task. The task success rate with attack, which indicates if we compare these two, how much the performance will degrade when an agent is confronted with attacks. And finally, I think the most interesting thing here is the stealth rate. The stealth rate is something very important in agent security because it highlights the percentage of tasks where both the task is successful, so the agent accomplishes what it should be doing, and also the attack is successful. So that it's very important because when you're monitoring your agent, something clear that your agent is failing is that the task success rate is very low. But if the agent accomplishes its tasks successfully, it might be harder to find that it's doing something malicious along the way. And we find that in some cases, like for example in the catalog, the stealth rate can be as high as 18%. The overall trend we see is that the task success rate will generally degrade when there is a presence of an attack, but not always in a very dramatic way. Sometimes it's 3%, sometimes it's a lot more. So we see a lot of variability in the resistance to attacks and between models, but also between different settings. So I think that the key takeaway message from these results is that depending on the setting, a model can be safer or more or less. Like if we look at the malicious user, Claude is a lot safer than GPT-4o, but it's not the same thing as in the malicious catalog. So this really highlights the need for a framework like DoomArena that allows you to do a really granular evaluation of agent security. So we're coming near the end. So I would like to close by saying that security evaluation is not separate from the evaluation of task performance. They're really both the same part of the same way of evaluating. Security testing needs to be grounded in the deployment context in order for you to really monitor the impact of adversarial interactions with the real deployment context. And finally, that's my shameless self-promotion. So DoomArena is designed for this, for real-world testing against evolving security threats. If you're interested in learning more, there's a link to the paper here. And if you're technical, here's the code.